All right. So which industries actually use Aspen HYSYS? Of course, oil and gas industries, chemical and petrochemical industries, pharmaceuticals and fine chemical industries, food and beverages, painting and coating. Load of lists. We have a lot of companies that use Aspen HYSYS. It's not like gas. We use Aspen HYSYS for gas dehydration, for gas compression, for production, a lot of things. So the thing is that each of these industries we've listed here, they make use of they make use of similar process equipment. Most of them here use distillation columns, they use reactors, they use separators. All these equipment are equipment that can be simulated on Aspen HYSYS. So as far as the equipment can be simulated on Aspen HYSYS, I can check the behavior of a plant directly from Aspen HYSYS. So Aspen HYSYS gives me an opportunity to actually see what is going on in the plant without actually going to the plant. Can we get the next slide? Okay, so enough of the theory. Let's get into the meat of the matter. So let me attempt to share my screen again. Can you see my screen?
Yes, we can see your screen.
Thank you very much.
Okay, well, he's visible now.
Thank you. All right, so I'm going to open a new case. So this is Aspen HYSYS interface. Still loading. All right. So this is Aspen HYSYS interface. Don't mind my laptop, please. Okay, I can work now. So now this is Aspen HYSYS interface. So everything here have their importance. There's a reason why they are there. So I will start with the properties side over here. So all items. Over here we have component list. So when you want to perform your simulation on Aspen HYSYS, of course you are dealing with chemical components. So over here the component list is where you are going to add all the components you are going to be dealing with in your simulation. For example, if you want to separate a mixture of water and ethanol with a separator, at this component list, you will have to add water and ethanol. So every chemical, every compound, every component you are going to be dealing with, you add them with the component list. And you're going to see how we use that as we go on. So now over here is the fluid package. Fluid package is basically the equation of state you want to use for your calculations in Aspen HYSYS. You know, in thermodynamics, in OAU here, we call it CH301. So in thermodynamics, before we do chemical engineering thermodynamics, yeah, we've been dealing with pressure, temperature, and so on. But then we've been using ideal conditions for our calculations. That's why we use ideal gas equation and so on. However, when we do chemical engineering thermodynamics, we have to deviate from the ideal situation and go a bit into the real life situation, because in the real life, in the real plant, the situation there is not ideal. So this fluid package consists of every equation of state you may want to use in your simulation. Peng-Robinson, Sarelic-Kwang, Van der Waal equation of state. All the equation of states we've dealt with in thermodynamics are here. So the equation of state we'll be choosing is dependent on the type of process you are dealing with. If you are dealing with hydrocarbon processing process, then Peng-Robinson is the most suitable fluid package to use. If you are dealing with maybe absorption using maybe MEA, maybe DEA, then NRTL and some other fluid packages are the best to use. So for you, before you can choose any fluid package, you have to be sure that the fluid package is actually compatible with the type of process you are dealing with. Over here we have petroleum acids. This is mainly for petroleum processing. Okay, I want to obtain the characteristics of a crude oil and so on. We are going to be looking at everything, and over here too we have informations about different crude oil around the world here in the petroleum acids, and I'm going to be taking you through that as time goes on. So reactions over here is where you specify the type of reaction you want to be dealing with in a process and the reaction equation. So if you are dealing with an equilibrium reaction, you specify it here and you also specify the equation. If you are dealing with a conversion reaction, conversion reaction, whatever reaction you are dealing with, you specify it here and you specify the reaction. So we have component maps, user properties. We won't really be using this here today. So let me come down here. We have properties. Properties basically everything I've explained earlier. We have simulation. So now after you've inserted everything you need for your simulation, because if I attempt to go to simulation without putting my component list, without putting my fluid package, without putting my petroleum acid when it is important, I won't be able to go to simulation. Well, before you can go to simulation, you need at least these two things at the top. You need a component list, listing all the components you'll be dealing with your simulation. I need a fluid package, the package or the equation of state you want your calculations to be done with. So look at it. If I attempt to go to simulation, I will not be able. Why? Because I have not specified my components and I have not inserted my fluid package. So this safety analysis, this energy analysis, well, today we won't be able to deal with this last two. We'll be mainly working with these first two and the first four in the properties. So I would like to go back to the slide, and I've prepared some problem statements that we can play around with. Please, can you still see my screen?
Yeah, no problem. Yes, I see your screen.
Thank you very much. So now we've dived into Aspen interface and we've seen how it looks like. So now let's play around with it. So this is a problem statement. It's a problem statement on a separator, a two-phase separator. You know, normally you have a two-phase separator, we have a three-phase separator. So, but for now we'll be dealing with two-phase separator. Well, after the simulation of the two-phase separator, we can adjust the problem so that we can work with a three-phase separator also. So look at this. A gas stream consists of 15% ethane, 20% propane, 60% isobutane, and 5% N-butane, normal butane. So this percentage is given in mole percent on molar basis. The stream enters at 50 degrees Fahrenheit and atmospheric pressure with a total molar flow rate of 100 pound/mole per hour. It is first compressed to 50 psi and subsequently cooled to 32 degrees Fahrenheit. The resulting vapor-liquid mixture is then separated into two product streams. Determine the flow rate and composition of the vapor and liquid streams. All right, so this problem is a good one because it's incorporated the use of compressor because our gas was compressed. It also incorporated the use of a cooler because our gas was cooled. So basically, this problem will be helping us to treat both two-phase separator, a compressor, and a cooler. First of all, when normally in Aspen HYSYS, a lot of things a lot of us do is that we just do our simulation, and when it converges, we are happy. However, you need to be sure that what you've done is actually going to happen in the real life, or what you've applied will be reasonable in real life. Looking at this, we have a two-phase separator. For me to be able to use a two-phase separator, it means my process stream, the inlet to the separator, sorry, the inlet to the separator have to be a two-phase inlet, a liquid and a vapor. If it is not in two-phase inlet, then using a two-phase separator will not be reasonable. I need to be sure that what I'm doing is actually reasonable to prevent loss of money, loss of profit, and unnecessarily increasing my capital cost. Because if I'm using a two-phase separator when it is not supposed to be used, I'll be unnecessarily increasing the capital cost of my plant. So we have a two-phase separator. So it means for us to be able to use a two-phase separator, it means we're actually working with two-phase, liquid and vapor. When we are dealing with three-phase separator, then we'll be dealing with liquid, vapor, and water. Well, maybe some of us have solid in mind, but one of the con of Aspen HYSYS is that it cannot deal with solid components. Aspen HYSYS can only work with liquid and vapor components. So it can't, Aspen HYSYS doesn't have the ability to work with solid components. Maybe in the future, maybe it will be incorporated, but at least for now, we can only work with liquid and vapor. So in three-phase separator, basically, it will be liquid, vapor, and water. So let's dive into this and play around with it. So let's see how we can get it done. So we have a gas stream consists of, can I go on? Are you together, please?
Yes.
Yeah, get
Yeah,
it.
we can hear you, sir. We can hear you, sir.
All right, thank you very much. Thank you very much. So now, a gas stream consists of 15% ethane, 20% propane, 60% isobutane, and 5% butane. So let's go to our Aspen HYSYS. So like I mentioned earlier, the first thing we do is add our component list. So I have my component list. I'm going to add. I'm going to click on add. So now look at this. I have a lot of chemical components here that I can add. A lot of them. Okay, not everything is showing. I just have to search for anyone that is not here and it's going to bring it for me. So from our problem statement, we are dealing with, what are the components we are dealing with? We are dealing with ethane. So I'm going to add ethane. So I'll click on it, then I'll add. We are dealing with propane. I'll click on it and I'll add. We are dealing with isobutane. That's ibutane. It's over here. I will add. And N-butane is over here, normal butane. Then I add. So I'm dealing with 4 components and I've added all of them. So the next thing I will specify now is my fluid package. So what fluid package do I want to use? Let's see, from our problem, were we given any specific fluid package to use? Let me share my screen again. Okay, no fluid package was mentioned. But I mentioned earlier that when we are dealing with hydrocarbon, the best fluid package for hydrocarbon is pengrobinsin. Well, Aspen HYSYS is a very beautiful software, such that if I attempt to add a fluid package that is not compatible with my process, depending on the components I've specified, it's going to give me warning. It's going to warn me, but I can go on if I want. So since I know that for hydrocarbon process, for hydrocarbon generally, the most suitable fluid package is pengrobinsin. So I go to fluid package, then I add, and I add pengrobinsin. So this pengrobinsin over here, see, we have a lot of fluid package. Can you see them? A lot of fluid package. So but I'm going to be using pengrobinsin for this problem. So I will click on pengrobinsin. So I've added my fluid package. Now that I've added my component list and my fluid package, I can now go to simulation seamlessly. Can you see that? I'm now in the simulation interface. So for you to be able to move to the simulation interface, you need to add your components and specify your fluid package. So over here, this is my simulation interface. So can you see this guy here that I'm moving around? This guy is called the model palette. As you can see, model palette. So it contains every process unit that we want to deal with. This is the mixer, the splitter, the heater, the cooler, the heat exchanger, the pump, valve, and so on, a separator, and so on. So this guy consists of all the equipment. See, we have a lot of them, a lot. In fact, Aspen HYSYS integrated important petroleum processing equipment. And so on now. See this one. No, that's okay. We have a fluidized catalytic reactor here. We have a delayed cooker. A lot of process equipment are in our model palette. So now, but even though I've specified my components, I've not defined my stream. My stream will be made up of the components I've specified based on the given percentage, based on the given fraction. So the first thing I do, so this blue arrow is the material stream, while the red arrow is the energy stream. Are we together? So now, since I'm trying to specify the components I've inserted earlier, then I will bring out my material stream. So this guy over here is my material stream. So this stream will be containing all the components I've specified earlier. So if you double click on it, so we have this. So let me just call it, you can rename it if you want. Automatically, Aspen HYSYS will give it a name using numbering. So you can rename it if you want. So I'll be naming this gas mixture. So now, just with any thermodynamic problem, before you'll be able to solve a thermodynamic problem, you have to specify two intrinsic properties. You have to specify two intrinsic properties. That is specify temperature and pressure, or maybe temperature and which other intrinsic property do we have here? Temperature and molar entropy. No, intrinsic property are not dependent on weight. So aside temperature and pressure, any component that you see in per mass is also an intrinsic property. Molar per mass or per mole, let me say per amount. So molar enthalpy is an intrinsic property because it is in per mole. Molar entropy because it is in per mole. So I either specify temperature and pressure, or temperature and molar enthalpy, or temperature and molar entropy. I just have to specify two intrinsic properties. So in this case, let's go back to our question. We can see that we are given temperature and pressure. It was mentioned that the stream enters at 50 degrees Fahrenheit and atmospheric pressure. So we are given temperature and pressure. So they've given us two intrinsic properties. So let's come back to our simulation and insert the temperature we are given. So we're given a temperature of 50 degrees Fahrenheit. So 50. So Aspen HYSYS give me option to manipulate or navigate around my units. So there are two ways of changing unit on Aspen HYSYS. So is either you enter your value and change the unit over here, or you change the unit of your calculation entirely by coming to the unit set over here. That is the unit set. So we have a lot of properties over here, so I can change the unit as I deem fit. For example, this is an angle, so I can change it to whatever unit I want to use, degree, radian. This area, I can use whatever unit I want to use. So, and a lot of it. My temperature, this is my temperature over here. I have temperature, so I can change the unit if I want. So, but since we are just dealing with a simple problem, there's no need changing the unit of the entire thing. So I can just manipulate around my unit here. So I'm dealing with 50 degrees Fahrenheit. As you can see, 50 degrees Fahrenheit is equal to 10 degrees Celsius. So my pressure, so I'm working at atmospheric pressure. So that means I'll be inserting 1 atm. 1 atm since I'm working at atmospheric condition. So now, normally after inserting my temperature and pressure, all my intrinsic properties are meant to be calculated. But why is it not calculating? So let's see. We have unknown composition. So it implies that I've not specified the fraction of each of my components that I've specified earlier. So this is condition, so I will come to composition. This is where I'm going to put the percentage, the fraction of each of the components. So it was mentioned that ethane is 15%. So you also have to be sure of the basis you are working with. See, I'm working with mole fraction basis. Depending on the question, you may have to change your basis, or depending on the process you are dealing with. So this is where you change your basis. Over here, we have mole fraction basis, which is what we are working with. Mole percent, mole fraction, the same thing. In this case, mass fraction, liquid volume fraction, mole flow, mass flow, liquid volume flow. So these are the bases you have over here. So depending on the question, you can work around any of them. So ethane is 15%. So that's 0.15. So propane is 20%. And that's 0.2. Isobutane is 60%. And that's 0.6. Then N-butane is 5%. And that's 0.05. So automatically, HYSYS has calculated it to be 1, which is what we are expecting. The total fraction have to be 1. So, okay. Now let's come back to our condition. All intrinsic properties would have been calculated. See, the vapor or phase fraction. Our phase fraction is 1. It means all our components are in gaseous state. We don't have any liquid in our stream. See this guy, an intrinsic property calculated, molar enthalpy calculated, molar entropy calculated. Why? Because they are intrinsic properties. Because they are not dependent on mass. They are not dependent on flow rate. Irrespective of the flow rate I specify, these guys are constant. So if I come to properties, every intrinsic property here have been calculated. Every property have been calculated, and that's because they are intrinsic property. If you look at everything here, they are in per amount. This is in per volume. API density basically is in per volume. Volume, okay, volume is in meter cube, and that's why it is empty, because it is not an intrinsic property. So it is not calculated. It is in per time. It has no per amount, and that's why it is not calculated. Mass enthalpy calculated, mass entropy calculated. So every intrinsic property have been calculated. So over here I have CO2 loading. I have no CO2, so obviously empty. CO2 apparent molar concentration, empty. So let's come back to our condition. So immediately I specify my flow rate, irrespective of the flow rate, maybe molar flow rate, mass flow rate, volumetric flow rate. Every other things will be calculated. So let's come back to our problem and see what was the flow rate given to us. Sorry. So the flow rate we are given here is with a total molar flow rate of 100 pound mole per hour. So we are dealing with, so our flow rate was given in molar basis, and it is 100 pound mole per hour. So we simply come back to our simulation and insert molar flow. So we have molar flow. You can enter either of these, either of any of these guys remaining. You can enter molar flow, you can enter mass flow. Anyone you enter, we automatically calculate the remaining properties. So I was given molar flow of 100. Is it 100? Let me confirm. Yeah, 100 pound mole per hour. So my unit is in kilogram mole per hour. Can you see that? Kilogram mole per hour. So, but that's not a problem. So 100, and I'll change my unit. See, I have different units. So I'm dealing with pound mole per hour. So, and this is it over here. So, okay. and everything has been calculated. Then I'm bullish, I have green. So as soon as you have green, it means you've converged your your simulation. So this process stream has been converged. So I know everything about this stream. Okay, so normally in our thermodynamics we make use of steam table, properties table. So whatever it is you want to check on your property table, that property table, whatever it is you want to check, Aspen HYSYS can simply give you by just specifying the temperature, the pressure, and the molar flow rate of your stream. Look at it. These are things I will naturally carry my steam table and be looking for. Everything is over here. That's the beauty. That's one of the beauties of Aspen HYSYS. I can easily obtain the properties of my stream just by specifying three things. And look at it. Every property I'll be checking steam table for. Where I can even make mistake. So this is my gas mixture. So our aim. So let's come back to our question. So the stream, okay, it is, now look at this, it is first compressed to 50 psi. Normally we are working at atmospheric pressure. So it was stated that that stream was compressed to 50 psi. So let me come back to my simulation. So compress, it means I need to bring in a compressor. So to do that, I will come over here to my model palette and I will search for compressor. This is a pump. Okay, let's search compressor. Compressor. So this is a compressor over here. Can you see that? So I bring it in. And of course, can you see the symbol? So the symbol justifies its name. It compresses. That is, it reduces volume. Can you see? It reduces volume. The inlet is bigger, the outlet is smaller. So basically a compressor. The opposite will be an expander. And for an expander, we expect the shape to be the invert of this. All right, so the gas was compressed, so I'm sending this gas to the compressor. So this is my compressor. So if I double click on this, so these are the things I have to specify. I have to specify the inlet of my compressor, what is actually going into it, and that's my gas mixture. So my fluid package is basis 1. So in a case where I'm dealing with different process units that uses different fluid package, I can change my fluid package over here. All right, so my energy, I'll just put anything. I'll just put an alphabet. I'll just put the name of this, basically an energy stream. I want to name my energy stream. So because okay, let's see. Let me call it Q1. Q1, that's my energy stream. And my outlet, let me say compressed gas. So let's come back to our interface. Look at it. So this is the gas mixture entering the compressor, and this is my compressed gas going out. This is the energy required to compress the gas from this inlet to the outlet. So let's go back. You see that this guy is still yellow. It's not converged. That's because we've not specified every necessary thing. Okay, so where were we? Okay, so now that we've specified our pressure, everything has been calculated and our simulation is converged. So we have green. So that's go. We are ready to go. Okay, so now if you look at this was the gas mixture that was entering the compressor, and this is the compressed gas going out of the compressor. Let's see, do we have any difference? So I will click on my compressor and go to my worksheet. So what difference can you see? You discover that when the temperature, when I increase the pressure from 14 to 50, from 14.7 psi, that is 1 atm, to 50 psi, my temperature also increased from 10 to 57.59. So which means increase in pressure led to an increase in temperature, of course, which is what we expected from our um Boy's law. P1 V1 equals P2 V2. No, sorry, from our Charles law. Is it Charles law or general gas equation? So general gas equation, P1 V1 over T1 equals P2 V2 over T2. So of course, increase in pressure and temperature are directly proportional. So increase in pressure will lead to an increase in temperature. So let's come back to our question, which stated that so it is first compressed to 50 psi, which we've done, and subsequently cooled to 32 degree Fahrenheit. So the compressed gas was now cooled. So this is another, we have to bring another process equipment, which is a cooler. So let's see a cooler. So this is a cooler over here. So from the arrow, you see it is taking it out of the system. So this is a cooler. All right. So I double click on that. So the inlet to the cooler is my compressed gas. So to cool, the cooler is going to be losing some energy. So the amount of energy lost, let me call it Q2. So the outlet, let me say cooled. Let me just use cooled. So I have unknown delta P, that is unknown pressure drop. So let's come to parameter and specify our pressure drop. Let's see. Well, I may not need to stress myself. I can come to worksheets and go back to the question. I'm actually cooling to what temperature? To 32 degree Fahrenheit. So I'm cooling to 32 degree Fahrenheit. So I'll simply come back to my simulation and insert the temperature of the cooled stream to be 32. Sorry, that's pressure. So temperature 32 degree Fahrenheit. And it was converted to 0, which is reasonable because sorry, this was okay, so 0.00, so which is reasonable because temperature of 32 degree Fahrenheit is equivalent to 0 degrees Celsius. So it's still telling me unknown delta P. Let me go back to my question. They have information on pressure drop. So the resulting vapor liquid mixture is then separated. Okay, let me assume that since no information was given to me regarding the pressure drop, let me assume that there was no pressure drop. Is either I put the same pressure here, which is 50 psi, or I come to my parameters over here under design parameters here and put a pressure drop. So since I'm assuming there's no pressure drop, I'll put a pressure drop of 0 and everything will be green. So I've successfully cooled the compressed gas stream. So let's come back to our question. And it was stated that the resulting vapor liquid mixture is then separated into two product streams. Determine the flow rate and composition of the vapor and the liquid streams. So let's see this stream. How do we even know that it is a two-phase liquid? It is a two-phase stream. So I will double click on the cooled stream, and from here, if you look at the vapor or phase fraction, you see a value of 0.2334. This is the percentage of vapor in this stream. So which means this stream actually contains both liquid and vapor. If the value here is 1, it means this stream contains only vapor. If the value here is 0, it means this stream contains only liquid. If the value is either 1 or 0, then it doesn't make sense for me to use a two-phase separator because what I'm dealing with will be in one phase. But since I have a vapor fraction of 0.2334, it means I have both liquid and vapor. So the liquid part will be 0.7776. Sorry, 7666. So it means I have both liquid and vapor, and it is reasonable for me to use a two-phase separator. So I'm simply going to come to my model palette over here and search for separator. Well, I may not need to search. This is it over here, separator. So I'll bring it out. So I want to separate this stream into liquid and vapor. Then I'll double click on the separator. The inlet to the separator is my cooled stream. So I send it in. So my vapor outlet, I can call it vapor, whatever, I can call it V or an L. Then this guy is my liquid outlet. So can you see, guys, it's calculated my answer for me directly. Now looking at this, if you look at what we've been doing earlier, For my compressor, I have to specify an energy stream. For my cooler, I have to specify an energy stream. That's because these process units are energy intensive stream. These process units are energy intensive units. So it is important for me to specify an energy stream. While for my separator, the energy stream is optional because it is not necessary that I specify an energy stream. So if I decide to specify an energy stream, then I will have to put the value. If I should put an energy stream here, then my simulation will be unconverged. Why? Because it will be required of me to put the value of my energy stream. So since I don't have to add an energy stream, I can just remove this and I have my converge simulation back. So, okay. Don't want to converge. Let's remove this. Okay. Let's see. We don't want to go. So this key is refusing to leave, but it has to leave. It must leave. Okay, looks like it has left. So what if it's not leaving? Ask me to put it. Well, it's not a problem. If it's refusing to leave, then we manipulate around it. So what can we do? Since I know that I'm not actually specifying any energy stream, I can just make the value 0. Then I have my convert simulation back. Another thing I can do is I can simply come here, as you can see, come here to the stream, to this stream, right click on it and break the connection. Right click on it and break the connection. So, and I can delete it. So, and here I have my separator, as you can see. So now, look at what Aspen HYSYS have done for us. It helped us to compress our gas. Normally, if you are working with material and energy balance, to do this compression alone is a lot of work. You have to go and carry your material table, your property table for each of the gases that are here. Then you start saying energy in equals energy out, bringing in enthalpy and so on. But with the use of Aspen HYSYS, it successfully calculated everything for us just by specifying temperature, pressure, and few other stuffs. So the same with the cooler, we would have started using our energy balance, and here it successfully separated this guy for us. And this is the beauty of Aspen HYSYS. So that's because I've not listed my components and I've not stated the fluid package I want to use. So over here, I'm going to list my components. Whatever component I'm going to be dealing with, I'm going to list them here. Then fluid package. Like I mentioned last week, fluid package is basically the equation of state with which we want Aspen HYSYS to calculate to perform our simulation. From our chemical engineering thermodynamics, we all dealt with equation of state where we talked about Van der Waals equation. Normally, in the preliminary thermodynamics, the main equations we use for our thermodynamic properties is the ideal gas equation. However, in real life is not ideal. So some scientists came up with other equations that actually relate the thermodynamic property close to how it is in the real life. So examples of those fluid package, we have Penn-Robinson, we have Van der Waals equation of state, we have Redlich-Kwong, we have a lot of them. So over here, the fluid package, this is where you're going to be choosing the fluid package, the equation of state you want your calculations, you want Aspen HYSYS to do your calculation with. So, and we don't just choose any fluid package. We choose fluid package based on the type of process we are dealing with, also based on the type of components we are dealing with. If we are dealing with hydrocarbon, the best fluid package to choose is Penn-Robinson, like I mentioned last week. However, if we are dealing with other processes, maybe absorption using maybe MEA or DEA, you are going to be using another fluid package, maybe an RTL or something. So if you choose the wrong fluid package for a particular process after you've listed your components, Aspen HYSYS will give you a warning. Aspen HYSYS will give you a warning, so you can correct the fluid package. However, if you want to go on with it, you can still go on with it. So the fluid package you are going to be choosing is dependent on the type of process you are dealing with. So we also have petroleum assay. Over here, we have
the data of a lot of crude oil from different countries, Nigeria, any country, most country, Venezuela, and so on. So we have informations about different crude oil in different countries. We have escravos information here. We have a lot of crude oil, Then we have reactions. So if you are doing reactor modeling, this is where you are going to be specifying the reactions, the type of reaction you want to deal with, maybe equilibrium. You are going to be specifying all of them. So let's just go straight to the problem statement we have at hand. Then we can explain further every other thing we are going to be doing with the problem statement. So let me go back. To the problem statement. Okay, so a gas stream consists of 15% ethane. So the components we are dealing with here are ethane, propane, isobutane, and N-butane. So I will go to my component list and put all these components. I'll go to my component list and put all these components in my Aspen HYSYS. So, sorry, please. So I'll put all these components in my Aspen HYSYS. All right, so component list. So we have it here. Then we go to add over here, down here. So we click on add. And after that, you have a lot of components over here. You have a lot of components. Look at it. You have a lot of components. So you are going to list out the components you are going to be dealing with. So from our question, the components we are dealing with are, we are dealing with ethane. So I'm going to, this is ethane over here. I'll click on it and add it to the component list. We are dealing with propane. I'll click on propane, add it to the component list. We are dealing with isobutane. So that's I-butane. I'll click on it, add it to the component list. Also N-butane, add it to the component list. So these are the components we are going to be dealing with in this simulation. So we have to add all of them. And after adding, like I mentioned earlier, the next thing we do is go to our fluid package to specify the equation of state you want to use to, you want to ask an ice. Can you still see my screen?
I can see your screen.
Thank you. All right. So fluid package over here, we add. So you are going to have a lot of fluid package. Look at them. A lot of fluid package. So we are dealing with hydrocarbon process. We are dealing with hydrocarbons. So the best fluid package to use is pengrobinsin. So we search for pengrobinsin. Where is it? Is it over here? So pengrobinsin. So I'm successfully choosing our fluid package. So we've listed our components. Here they are. And we've chosen our fluid package. So we have chosen pengrobinsin fluid package. So now that we've listed our components and we've chosen our fluid package with which we want Aspen HYSYS to do our calculation, then we can go to simulation. So we can go to simulation seamlessly now. So we are now in the simulation interface. So we are in the simulation interface. So now after listing your components and adding your fluid package, then you can go to the simulation. So here we are. So this guy over here that I'm moving around is called the model palette. Over here is where you have all your unit operation, all your equipment. This is where you pick them from and add them to your flow sheet. So this is the, as you can see, this is the mixer, the splitter, the heater, and so on. We have a lot of equipment here. So this blue arrow, this blue line, this blue arrow here is the material stream. And this red arrow is the energy stream. And this guy here is the power stream. So we are dealing with a mixture of ethane, propane, butane. So I'm going to bring out my material stream so that I can impute the composition of each of the components we are dealing with. So I've brought out my material stream, then I will double click on it. And okay. So I have it over here. So I'll double click on it. So these are my, okay, let me go to composition. So we have it here. So these are the substances, these are the components you are dealing with: ethane, propane, iobutane, N-butane. So according to how it was given in our problem statement, we are going to insert their compositions. So the composition is based on mole percent. If it is based on maybe mass percentage or maybe volumetric percentage, we can change it here. We have edit. Let's say you forgot to add a particular component, you can edit. Then okay, if you want to add the composition, so if you want to add another component, just go back to properties and add the other components you've maybe forgotten to add. So over here we have edit, we have the properties, we have basis. So here we are dealing with mole basis, mole percent, but you can change it depending on the type of question. So you just change it over here, click on basis. Your basis can either be mole fractions, mass fractions, liquid volume fractions, mole flows, mass flows, liquid volume flows. So depending on the problem statements you are dealing with, or the type of process you are dealing with, the type of data you are given. So over here we are dealing with mole percent, so I'm going to be dealing with mole fraction. So ethane, from our question, ethane is 15%. The stream contains 15% ethane. So I'll come here, ethane, and I'll put 0.15. 0.15 for ethane. Then for propane, I have 20% propane, so I'll put 0.2 for propane. Then for iobutane, I have 60% iobutane, so I'll put 0.6. And for 0.6. And for N-butane, we have 5%, so 0.05. So if you look at this, the total is 1. That has to be 1. If the total is not 1, Aspen HYSYS will normalize it automatically based on the weight of the fractions you've added. So we've added our composition. So okay, then we come back to condition. So like I mentioned last week, for you to be able to, for Aspen HYSYS to be able to calculate anything, you need to specify 2 intrinsic properties. Is either you specify temperature and pressure, or temperature and, we know what intrinsic property is. Any property that is in terms of per amount, maybe per kilogram or per mole or per volume. So any property that is in per amount are intrinsic properties. So is it that I specify maybe temperature and pressure, or maybe temperature and let's say molar enthalpy, because molar enthalpy is also an intrinsic property because of per amount, per kilogram mole, or maybe molar entropy per kilogram mole degree Celsius. So you have to specify 2 intrinsic properties. So from our problem statement, we're given 2 intrinsic properties, and that's temperature and pressure. You know, they said the stream enters at 50 degrees Fahrenheit and atmospheric pressure. So they've given us temperature and pressure. So those are the 2 intrinsic properties we've been given. So for you to be able to use Aspen HYSYS, you need to feed Aspen HYSYS with 2 intrinsic properties. So here I'm given temperature and pressure. So 50 degrees Fahrenheit, we have 50 degrees Fahrenheit. So you can change your units. So there are 2 ways of changing your unit. Is that you change your unit after inserting the value, then you change the unit with the drop down over here, or you can change your unit set entirely. Is it over here? Change your unit set, and you see unit set over here. So these are the properties, different properties over here. Then you can choose whatever unit you want to work with. So let me just change it over here. So I have a temperature of 50 degrees Fahrenheit. So 50 degrees Fahrenheit, I have that over here. So it changed to 10 because my normal temperature basis is in degrees Celsius, so it automatically converted it to degrees Celsius. And 50 degrees Fahrenheit is 10 degrees Celsius. Then pressure. My pressure was given to be atmospheric pressure. Atmospheric pressure, that was 1 atm. So I'm simply going to have 1 atm. So this atm over here. So since the basis of pressure is in kilopascal, so it's converted the 1 atm to kilopascal, which is 101.3 kilopascal. So now, after you've inserted 2 intrinsic properties, every intrinsic property in your Aspen HYSYS, every intrinsic property of your process will be automatically calculated. Look at this. Molar enthalpy has been calculated because it is an intrinsic property, because it is in per amount. Molar entropy has been calculated because it is an intrinsic property. It is in per amount. Look at molar flow. It's not calculated because it is not an intrinsic property. This is per hour, this is per time. So it's not an intrinsic property. It depends on the amount of substance you are dealing with. Mass flow is also not an intrinsic property. That's why it is not calculated. Standard ideal liquid volume flow is also not calculated because it is not an intrinsic property. Look at it. Let's come to property here. See, we have condition, property, composition, and so on. So if I come to property over here we have property of the stream we've specified. So every property here that are intrinsic property will be calculated. Every ones that are not, you see empty because I've not fed in enough information for them to be calculated. Look at this. We have molar weight calculated, molar density is in per month, per volume calculated, mass density calculated, mass enthalpy per kilogram, that's per month calculated, mass entropy per kilogram calculated. So every intrinsic property here has been calculated. Anywhere you see empty, it is not an intrinsic property. Look at the surface tension, it is in per centimeter. That's not an amount of substance. So every intrinsic property has been calculated. So if I want my other properties to be calculated, then I will have to specify one more thing, which is the amount of substance. So over here, it was given that the total molar flow rate is 100 mole per hour. So they've given us the amount of substance. So that's the molar flow. So I come over here and I put 100 mole per hour. The basic, the unit basis for molar flow here is kilomole per hour. So what I'm giving is in power mole per hour. So I'll change the unit, power mole per hour. Here, click on it. So I have green, means I've specified, I've imputed everything I have to impute, and Aspen HYSYS have successfully calculated every parameter I'll be needing. So I have them here. Now remember, when we're doing our thermodynamics, we use property table, steam table, a very popular one. Steam table where we have temperature and pressure. We'll be looking for other properties, maybe enthalpy, entropy, specific volume, and so on. One beautiful thing about Aspen HYSYS is that immediately you specify your temperature and pressure, you have access to all of those properties and more. Look at them here. You have access to all of those properties and more. So Aspen HYSYS is a very beautiful software. So everything we will be looking for, and the thing is that it's difficult to get the property table of some components. Imagine here we have, and more often than not, the property table are in terms of a single component. But here we have mixtures of components. We have ethane, we have propane, we have I-butane and N-butane, mixtures of components. Imagine you are trying to use property table to obtain these properties. That would be a very tedious and difficult task because we have to be checking for the property of each of the components and be working with the basis given and everything. That would be a very tedious work. But look at it, Aspen HYSYS have successfully given us all those results without stress, simply by inputting temperature, pressure, and the composition. That's how powerful Aspen HYSYS is. So now that we've specified our components and the composition, and we've inserted the okay, let me rename this. Let me call it feed stream. So over here, this is your stream name, so you can rename it feed. Okay, let me just leave it as feed. So now the next thing, let's go back to our question. The stream enters at 50 degree Fahrenheit and 1 atm atmospheric pressure with a total molar flow rate of 100 mole per hour, which we've done. It is first compressed to 50 psi. So we need to bring in a compressor. So we are in, of course, compressed to 50 psi because we are trying to increase the pressure. So we need to bring in a compressor to compress the feed. It is in 1 atm. We want to compress it to 50 psi. So to do that, so look at it now. My model palette, I can't see it. So to bring back my model palette, I'll simply click on F4. F4 is the shortcut to bringing back your model palette. I'll click on F4 and I can have back my model palette. So in some computers, it may not be F4, it may be Fn and F4 together. You have to press Fn and F4 together. And well, if you don't want to do that, there's another way you can bring back your model palette. So you can simply come to flow sheet. Oh, is it flow sheet? Sorry, please. Come to view over here. We have view over here, then you click on model palette and you're going to have it. So is it that you use the shortcut F4? In some computers, it may be FN F4, in some PC, FN F4. But if you don't want to do any of that, just go to view and click on model palette. So if I cancel it, it goes. If I want it back, I click on it. So I have my model palette. So I want to bring in a compressor to compress this feed to 50 psi. So I simply search for compressor. Cut it over here. Compressor. So I'll bring it. So I bring my compressor and so double click on it and I feed in. Let me bring this. So double click on it. So the inlet to the compressor is our feed. So you drop down and you click on feed. So the outlets, let me say compressed feed, or let me say compressed or anything, because that's compressed. So that's the outlet. Now, this guy is asking for energy stream. So because for you to compress from 50 to from 1 atm to 50 from 1 atm to 50 psia, your compressor must have done some work. And for you to do it won't just do the work alone. You need to supply some energy for it to do the work. So let's call that energy Q1. So that's the amount of energy supplied to the compressor. So, and we are compressing to 50 psia. So it means the pressure of this outlet stream is 50 psia. So to do that, I can come to worksheet over here and specify the pressure of the outlet. I come to worksheet. See over here we have the feed information and the outlet information. These are the inlet information to the compressor. These are the outlet information to the compressor. So I will simply insert the pressure I was given, which is 50 psia. So 50, and I'll drop down and change the unit psia. Yeah, over here. So I click on that, and my outlet has been automatically calculated. So here we go. So I've successfully compressed my feed from 1 atm to 50 psia. So after compressing, let's come back to our question. It is first compressed to 50 psia and subsequently cooled to 32 degrees Fahrenheit. So which means we need to bring in a cooler. So to cool it, see the temperature right now. The temperature is at look at it, 57.59 degrees Celsius, which is equivalent to 135.7 degrees Fahrenheit. So I want to cool that to according to our question, 0 degrees Celsius. That's 32 degrees Fahrenheit. So I'm going to bring in my cooler. So I will search for cooler, my model palette, cooler, my model palette. I have it over here, so I'll bring it, double click on it, bring this here. Okay, I should just place it on. All right, so these are the design informations of my cooler. So what's the inlet to the cooler? That's my compressed feed, my compressed gas mixtures. So I'll click on compressed. My outlet, let's say cooled, don't mind my name, is cooled compressed. You can give it anything. And energy, for you to compress, you also need energy. So let me call that Q2. So let's come to worksheet. Since I'm cooling to 32 degrees Fahrenheit, so I'll come to worksheet and input that outlet temperature, which is 32 degrees Fahrenheit, which is equivalent to 0 degrees Celsius. So, and also my pressure still remains what it is, which is 50 psia. So the cooler, the only work it was set, it is doing according to our problem statement is that it is cooling to the 2 degrees Fahrenheit. So my pressure remains 50 psia. 50 psia as given to us in the question. So 50 psi. So we have green, which means all the properties of this fluid has been, of this stream of this cooled comp stream has been calculated. So we successfully compressed and cooled. So what's the next thing? Let's come back to our question. So the resulting vapor liquid mixture is then separated into two product streams. So like I mentioned last week, for you to be able to separate using, into two product streams. So basically, into two product streams, we are basically using a separator. It's separated into two product streams. We are basically using a separator. And for you to use a separator, your stream must be in two phases, liquid and vapor phase. We have type of separators. We have two-phase separator and we have three-phase separator. Two-phase separator is going to be separating into liquid and gas or vapor. Then be separating into liquid and gas. While three-phase separator will be separating into liquid, gas, and water. So we have water, liquid, gas, and water. That's what three-phase separator does. It separates into liquid, gas, and water. While for two-phase separator, it simply separates into liquid and vapor. So now I'll bring in my separator from my model palette. So for me to be able to separate, I must be sure that this thing is actually in two phases. So let's see, is it actually in two phases? Do we have two phases? So let's come to our code com. Let's see. To know that, we can come to the vapor or phase fraction over here. So at the vapor fraction, we have 0.2334, which is 23.34% of that stream is vapor. So, which means we can actually use a two-phase separator because we have two phases. And if this guy here is 0, which means there's no vapor, or 1, which means there's no liquid, then it won't be reasonable using a two-phase separator because what you have is in a single phase. So since we have confirmed that we have two phases, which is liquid and vapor, then I can bring in my separator. Here it is, over here, separator, a two-phase separator. So I bring it in. So I have this. So the inlet to my separator, sorry. Okay, let me just. The inlet to my separator is the cool comp, this guy over here. So for the separator, you can send in as much inlet as possible. But here we have only one inlet, which is the cool comp. So I will send it in to the separator. Then the vapor outlet, let me call it VAP, VAP. And the liquid outlet, let me call it LIQ. So I have that. Okay, so my energy is optional. So your separator, oh, this guy, enter. So my energy is optional. So I don't necessarily need to So I want the separation to be done at adiabatic condition. That is, I don't want to add any heat to this system. So if you want to add heat to the system, you can simply do that and insert Q3 or something. So Q3, then you go to your worksheet and specify the amount of heat you want to supply or remove from the system using the sign positive or negative. But yeah, I want to work adiabatically. So I'm not going to be specifying any energy stream because it is even optional. So I can cancel that, and I've successfully simulated this process we have here. We've successfully simulated that. So now let's go to the question. They said determine the flow rates and composition of the vapor and liquid streams. So the flow rate and composition of the vapor and liquid stream. So I can come here, click on the vapor stream. So what's the flow rate of the vapor stream? Molar flow is 10.59 kilomole per hour. So if you place your cursor on it, you can have your answer in different units. It's also equal to 23.34 per mole per hour. So that is the flow rate of the vapor stream. What of the liquid stream? Double click on it. So we have it over here. The flow rate of the liquid stream is 34.77 kilomole per hour. So this is the flow rate of the molar flow rate of the liquid stream. If you want it in per mole per hour, you have 76.66 per mole per hour. So the flow rate and composition. So to get the composition of the liquid, so we will simply come to, see we have condition properties, we'll simply come to composition over here. Click on composition. So these are the compositions. So these are the composition. So okay, let me just click on my separator and come to worksheets. So these are the flow rate. This is the flow rate of the liquid, the flow rate of the vapor. So if I want the composition, I can simply come here. So these are the compositions of the liquid, these are the compositions of the vapor. So ethane, the composition of ethane in the liquid is 0.0731, while at the vapor is 0.4026, which is reasonable. Because of all these components we have here, ethane is the lightest. So it is expected that ethane will be the most converted to vapor. And of course, it will come out as vapor the most. And that's what we can see here. We have ethane to be much here. Look at propane follows at the vapor, then butane, iButane follows. So N-butane, of course, we'll be expecting something similar to iButane. However, if you look at the composition of N-butane that we have, it is 5%. We have a very small amount of N-butane. A very small amount of N-butane. So that implies that it is not, we shouldn't expect that the value here will be comparable to the value of iButane. See the percentage of iButane, isobutane, we have 60%, while N-butane is 5%. So the amount of N-butane in our stream originally is very small. So we don't expect the composition to be large. So over here we have, these are the compositions of the liquid. This is the ethane, this is the propane, this is the iButane, and this is the N-butane. So we have successfully simulated the problems, the given process, and we've obtained. So you can obtain any result you want. You can obtain any result you want, any information you want about this process. So, and that is that about this problem statement. Before we go on to the next problem statement, I would like to, maybe we should leave questions till the end of our section. So let's see the next problem statement. So here we have successfully simulated a two-phase separator, which incorporated a compressor and a heater, and we have been able to separate them into two phases: the vapor phase and the liquid phase. And that is that about this problem statement. Now, if you want to solve all this by hand, which is actually possible, this will take you a whole day. Because we have to do material balance, we do energy balance. You have to go and look for property table of each of the components we are dealing with. You're going to be doing a lot of work. But look at it, just in how many minutes Aspen HYSYS have done that beautiful job for us. So that's the beauty of Aspen HYSYS. Simulates, it gives you a virtual plant to that way, and you can test for anything. So before I move to the next example, let me use this to explain one beautiful thing that Aspen HYSYS can do. See over here, I can do some variations. I can do some variations in my feed, and with that variation, I can use it to check what will happen to my vapor. What happens as I increase the flow rate of my feed? When I increase the flow rate of my feed, what actually happens to my vapor? Or let me say, what happens to a particular component in my vapor? So to do that, we can simply come to what we call workbook over here. Sorry, case studies. So I want to see how each of different properties, how they vary with another property. How's the relationship between two or more properties? So I can come to case studies over here. Click on case studies. So click on case studies, then you add case study. So now, here in the case study, you have independent variable. I have the dependent variable. The independent variable is the variable you want to vary. And the dependent variable is the variable you want to see its response to the variation in the independent variable. Basically, I'm trying to understand the dynamics of this process. So I want to understand the dynamics of this process. When I vary the feed, what actually happens to the, let's say ethane at the vapor phase, or maybe ethane at the liquid phase or something. So yeah, I have independent variable. That's the variable I want to vary. Dependent variable, the variable I want to see its relationship with the independent variable. So I come to variable manager over here. This guy. Oh, sorry, come to find variables. I'll come to find variables. So the variable I want to vary is the feed. Or maybe let's say I want to do something, the feed. I want to deal with something in the feed. I want to vary something in the feed. So let's say I want to, so these are the properties you can vary. Look at them, we have a lot of them. And vary, blah, a lot of them, we have a lot of them. So let's say I want to vary, let's say molar flow. I want to vary molar flow of the feed. I want to vary molar flow of the feed. So I'll click on molar flow, then I'll click on this arrow over here. So I have molar flow, then done. And I'll come to my dependent variable. I'll come to my dependent variable, come to find variables. So I want to see the response of this variable to the variation in my feed. Let's say I want to understand the variation of temperature of the vapor with the molar flow of the feed. So I have my vapor. Where is it? Is it over here? I have my vapor. Then these are the properties I can see their relationship with the molar flow of the feed. So let's say I want to see the temperature. Temperature should be down. Temperature. Here it is. So I want to see how the temperature of the vapor varies with the molar flow of the feed. So I'll click on temperature and I can add that over here. Then done. So I want to see how temperature varies with molar flow. So now this is the current value of the what's it called, of the feed. So I can come to case study setup. So here in case study setup, I will put the range of values of the molar flow with which I want to use. So let's come to case study setup. So look at it. This is the current value, 45.36. However, I want to see what happens. Since I want to understand the relationship of the molar flow with temperature, then I have to input a lot of values. So let's say I start with maybe 10 kilomole per hour, and I want to end at, let's say 80 kilomole per hour. As you can see here, enter with a step size of, let's say 5. At this, I want to see the value of temperature at 10 degrees, at 10 kilomole per hour, at 15 kilomole per hour, at 20 kilomole per hour, up to 8 kilomole per hour. So I have the step size. Enter. So I have 15 steps in all. So after that, I've set this up already. Then I can click on run. I can click on run, and it has worked successfully. So let me come back to results. So you set that up, case study setup, then you've run. See, you have green success. Then you can come to results. Look at it. So when my feed flow is 10 kilomole per hour, temperature is 0, which means the feed flow, the temperature of the vapor is independent of the feed flow. And what do you think is the reason for that? Let's come back to our flow sheet. Over here at the cooler, we have cooled the inlet input to this separator to 0 degrees Celsius, that's 2 degrees Fahrenheit. So we've cooled this guy to 32 degrees Fahrenheit, which means irrespective of the amount of feed I'm sending in, this cooler will always cool it to 0 degrees Celsius. And that implies that this vapor and this liquid will always be 0 degrees Celsius because the cooler has already cooled the inlet to 0 degrees Celsius. And this process, this separator, is not an energy intensive process. I'm not adding energy and I'm not removing energy. So which implies that the temperature of this inlet will be the same thing as the temperature of these guys. So irrespective of what I'm sending in here, I'll be having this temperature over here. So that's basically how to use case study. You can see the relationship between two properties by simply going to case study, select your variables, set up your case study by inputting the start and end values of your independent variable. Then you run and go to your results. So if you want to see the plot, look at it over here. I expect the plot to be an horizontal line. Look at it. So because my temperature is always 0, vapor temperature is always 0, irrespective of the flow rate. So we have an horizontal line, as you can see here. So that's basically a beauty of Aspen HYSYS. You can see the relation between two or more properties by simply going to case study and setting it up. All right, so let's move to the next problem statement before our time runs out. So I believe everyone here can now model a two-phase separator and you can do some analysis on it to see some variations and appreciate the beauty of Aspen HYSYS. So let's go to another problem statement. So we want to simulate a simple distillation column. A distillation column is one of the most important process units, one of the most important process equipment in chemical engineering, chemical industry. distillation column is just very, very powerful. And modeling distillation column by hand. Okay, sorry, let me share my screen to the next problem statement. So share. So let me share my screen to the next problem statement. So we are here we go. So our simple distillation column. So distillation column is a very, very powerful process equipment. It is used in almost all chemical, petroleum and petrochemical process. So now, of course, a lot of this equipment we can model them by hand, but we are going to be putting ourselves through a lot of stress. If you want to model this simple distillation column and you want your model to be robust, you want to have a very beautiful model that actually defines your distillation column, you are going to be doing a lot of work. And what is the reason for that? Distillation column is an extremely non-linear equipment. Distillation column is one of the most non-linear equipments. For those of us that have done process dynamics, control, and instrumentation, I think we are going to understand what we mean by non-linearity. Distillation column is very non-linear. So for you to model distillation column by hand, it is going to take a lot of work, a lot of linearization, a lot of work. And at the end of the day, you might obtain a model that deviates slightly from the actual model of your distillation column. So instead of putting ourselves through that stress, Aspen HYSYS can simply reduce that load for us and sort this problem without much stress. So we have our problem here. Simple distillation column. We need to separate a mixture of 5 paraffins into light and heavy fractions by using a distillation column with 12 trays, a full reflux condenser, and a kettle reboiler. Of course, distillation column typically consists of your trays or packings. And what is the reason for that? For to give some resistance to your upward flow. So we have we have condenser and we have reboiler. These are typically the components of a distillation column. Then now the feed stream, which is 1,000 pound per hour, consists of 3% ethane, 20% propane, 37% N-butane, 35% N-pentane, and 5% N-hexane at 225 degrees Fahrenheit and 250 psia, which enters the column on the 6th tray, counting from the top. The condenser and reboiler pressures are 248 and 252 psia respectively. The preliminary design specifications require a reflux ratio of 6.06 and a vapor overhead product of 226 pound per hour. Subsequently, the design is modified to ensure propane overhead flow of 191 pound mole per hour and N-butane bottom flow of 365 pound mole per hour. Use SRK, this Sarelish-Kwang fluid package. Calculate the condenser temperature, the reboiler temperature, and the reflux ratio after modification. So here they want us to simulate and do some modification to obtain. This is the beauty of Aspen HYSYS. If there is no Aspen HYSYS and some other simulation software, this thing will have to be done in real life, which will be that will be a lot of cost and a lot of work. So, but Aspen HYSYS can simply do that for us without much problem. After the simulation, I still want to check one thing. I want to see, okay, I want to modify my simulation such that I'm going to have an overhead flow of 191 pound per hour and bottom flow of 365 pound per hour. Imagine there's no Aspen HYSYS. It means I'll have to be doing this thing with real life by doing trial and error. And I'm going to be wasting a lot of cost. Or well, maybe by mathematical modeling, which will be extremely difficult because distillation column is a very non-linear equipment. So without much ado, let's get to work. Let's get into our Aspen HYSYS interface. So let me share my screen. Let me share the Aspen. So let me present something else. entire screen. So let's come back to our HYSYS interface. So here we go. Okay, coming. Okay, so this, let me save this. Let me save this. Just if you want to save just your normal Control S. So Control S. Control S. Saved. Okay. So I want to open another flow. I want to open a new case. I'll come to File, New. So create new case. So create a new template. So I want to open another case. So here we go. So we are done with the first problem statement. So let's play around with distillation column. So we need to simulate a mixture of 5 paraffins into light and heavy fractions by using a distillation column with 12 trays, a full reflux condenser, and a kettle reboiler. So I'm dealing with the distillation column. Then a feed stream, this consists of, see, look at the components we have here. So like we've stated earlier, the first thing you do on Aspen HYSYS is to list your components. So I have component list, then I will add. I want to add all the components I'm dealing with. So which are here. So I have ethane, propane, N-butane. So ethane, I have ethane, I will add. I have propane, I will add. I have N-butane, I will add. I have N-pentane, I will add. And I have N-hexane, add. So I've successfully added my component. So the next thing is I'll go to my fluid package. So I'm adding a fluid package. So from the question, it was, we were told I should use Sir Redlich Quank. So SRK. So let's look for Sir Redlich Quank. Here we go. Over here. SRK. So we have specified our components and we've inserted our fluid package. Then we can move seamlessly to simulation. So here we go, simulation. So we have our model palette ready to work. Everything ready, set, ready to work. So the first thing I'll do is I'll bring my material stream so that I can put the composition and the property of my stream. So this is the material stream. Double click so I can rename it to feed to distillation column. Feed. So now from the question, it was said that the feed stream 1000 pound mole per hour consists of 3%. So let me go and put the composition. Let me put the composition. So I have 3% ethane. So ethane is 3%, that's 0.03. 20% propane. So propane is 0.2. 37% N-butane, 0.37. 35% N-pentane, 0.35, and 5% N-hexane, 0.05. So we have one dot. So okay. So I can come back to my condition. So once again, I would like to input the intrinsic property first so that you can see how every other intrinsic property will be calculated. So from here, I was given my temperature of the feed to be 225 degrees Fahrenheit. So I have 225 degree Fahrenheit, drop down, change the unit. Then I have 250 psi, 250 psi. So drop down, change the unit. Here you go. So now, if you look at it, all intrinsic properties have been calculated. Everything. So let me come to properties. Every intrinsic property has been calculated as usual, as expected. So let me come back to condition and input my feed stream, which is 1000 pound mole per hour. So my molar flow is 1000 pound mole. Pound mole is that pound mole per hour. Here we go. So this is our molar flow. So you see, we now have green. Everything has been calculated. Beautiful. So every property of that stream you want can be gotten from here. See, every property. This is what is going to be very, very tedious using property table. Okay, so now this guy was sent to the distillation column. So let's come to our model palette and bring in distillation column. So distillation column. So this is a simple distillation column. this three-phase distillation column. This one is already becoming something like a fractional distillation column when you have more than two outlets. But three-phase separated into three. We have shortcuts. This one you want most of the product to be at the bottom. So we have a lot. If you want to deal with fractional distillation, the best type of distillation column to use is your reflux. It's called reflux. So maybe you want to deal with petroleum refining. You want to deal with crude oil refining. The atmospheric distillation unit, ADU, is a reflux absorber. So here you can add a lot of pump around, a lot of side strippers with which you can remove different components. Okay, so it is the reflux absorber. So let's come back to our distillation column. So distillation column, here we go. So we'll bring this guy in. Oh, that's big. Let's reduce the size. Okay. So now, double click on that. So it was said that, so let's come back to our question. Which enters the column on the sixth tree? So first of all, how many trees do we have? Let's see. The condenser is this. I'm looking for the number of trees we have normally. Oh, at the top, we need to separate a mixture of 5 paraffins into light and heavy fractions by using a distillation column with 12 trees. So we have 12 trees. So I'm going to be changing this number of trees. So, okay, let me explain each of these terms here we have in the distillation column. This is the column name. This is the condenser energy stream. Of course, your condenser needs energy. This is your reboiler energy stream. Your reboiler needs energy. This is your. Now we have total type of condensation. You can have total condensation. Here, you don't want to remove anything as vapor. As you can see, immediately it enters, everything is condensed and it will be removed as liquid. So you don't want to remove anything as vapor. That's total condensation. You want to remove it as liquid. Partial condensation, you want to remove some as vapor and some as liquid. That's partial reflux. You want to remove some vapor and some liquid. While for full reflux, you don't want to remove any liquid. Everything you want to remove should be vapor. So total, you want to remove only liquid. Partial, you want to remove both vapor and liquid. And full reflux, you want to remove only vapor. So depending on the type of process you are dealing with and what you desire, that will be the judgment of the type of condenser you are going to be using. However, here they told us that we should use reflux. Okay, I'm coming. Sorry. Where's that guy? The preliminary design. So we are going to be using where's that guy? A full reflux condenser. So that was given to us in the problem statement. So a full reflux. So I'm going to be choosing full reflux. Okay, I choose that already. I'm going to be choosing a full reflux. So this N over here is the number of stages. So and I want my number of stages to be from the top. From the problem statement, it was mentioned that our feed enters stage 6. Where's that? Stage 6. Here's that guy. Design. Sorry. 6 tree, counting from the top. So I want my counting to be from the top. So 1 at the top, 2 up to 12. So I want to change the number of stage to 12 as given in the problem. So N is the number of stage 12. So, and I want my numbering to be top down. So I can either choose top down or bottom up. So I want top down since my numbering is from the top. So, and my feed is entering this distillation column at this automatically. Aspen HYSYS put it at the middle. So, but if you want to change it, just click on this drop down and change it. But of course, I want it at the sixth stage, and I've successfully done that. So my outlet, my overhead vapor. So I want to remove VIP. So let me call it VAP. And I want to remove bottoms. I'll call it, or let me say condense. No, I won't call it condense. I can call it distillate. So I want to remove bottom. Let me say BTM bottoms. I'll call this distillate. Let me call it distillate. DIST. Even though it is paper. Distillate. Okay. So now condenser energy stream. My condenser needs energy. So I'll put energy Q1. Or let me say Q cond. Q cont, and my reboiler, let me say Q re for the reboiler. So we've inputted everything we need to specify here. So let's click on next. So over here, really don't have to do anything here. So we just have different type of reboiler configuration. Carbons through circulation without baffle, blah blah blah. So once true has been automatically picked, and that's what we are going to be using. We don't really need to pick any other one. So the next. So over here, we are going to be specifying our condenser and reboiler pressure. So from the problem statement, it was stated that the condenser and reboiler pressures are 248 and 252 psi respectively. So condenser pressure is 248 psi, and reboiler pressure is 252 psi. 252 psi. Is that guy? Yeah, good. So specified everything we need. So my pressure drop, I'm keeping it at 0. I don't want the pressure drop from the previous statement. No pressure drop was specified or stated. So next. So yeah, I can input the condenser temperature and reboiler temperature if I want. It's optional. So I don't have to. It's optional condenser temperature. So I don't have to. I'll click on next. So yeah, vapor rate. Let me just, I don't know the value. I don't know the value of my vapor rate, or do I? Let's see. The preliminary design specifications require a reflux ratio of 6.06. See the reflux ratio here, 6.06. So we specify that. And a vapor overhead product of, okay, they give me an overhead product of 226 pound per hour. So this is my overhead product over here. So 226 pound per hour. So done that. So 226 pound per hour. So that's my vapor overhead rate. So done. So we've inputted everything we have to input, and we'll click on done. So this guy is not converged. So let's double click. Where are you? It's still loading. Where's that? Oh, he's here. So I'm bringing it here. So I have connections, monitor. So this page here is summarizing everything we've inserted into our distillation column. Every properties we've listed, summarizing everything. So I can come to monitor. So over here, the monitor is where I will specify some information with which I want to use. I want my Aspen HYSYS to run my simulation with. Over here, I've specified the reflux ratio and vent rate. That's the vapor rate. Now, for you to be able to run this, your degree of freedom must be 0. Of course, the number of unknowns minus number of independent equations, like we did in our basic chemical engineering. So reflux ratio is 6.06 and it is active. Vapor rate is active. So I have a degree of freedom of 0. So let me run and see if it will converge. And it's converged. Beautiful. So one thing about distillation column is that sometimes it can be very, very difficult to converge. So you keep varying your results, varying your values until you're able to converge it. So thank God we converge this ones with the information given. So successfully converge that. So let's go back to the flow sheet and see we have it converged. So, and whatever result you want from your distillation column can be obtained from this simulation. Whatever you want to know about the distillation column or about the product can be obtained from this simulation. So let's say our products. Let's see our vent rate, our distillation. Of course, since I'm removing it as vapor, I expect the phase fraction to be 1. That is totally vapor. And this is the temperature, this is the pressure. So these are the properties. Let's see the composition. We have ethane here. We have propane. Normally, we expect ethane to have higher composition. But if you compare the composition of ethane and the composition of propane that is entering the process, the composition of ethane entering propane is 3%, while for propane is 20%. So, since they don't have equal composition, then it's expected it might be expected that propane we have more combustion at the vapor phase, which is reasonable because the amount of propane we have is about 7 times the amount of ethane we have. And that is why the combustion of propane, even though should not be higher, it is higher than ethane because we have more propane in our stream. So these are the compositions and everything. So let's come back to our problem statement. We are not done. The problem statement now said that the preliminary design is specification require, okay, this. Now, subsequently, the design is modified to ensure propane overhead flow of 191 pound mole per hour and then butane bottom flow of 365 pound mole per hour. So, guys, this is actually the vapor flow rate flow. Look at it. The top flow, molar flow of, let's say, in pound mole per hour. It is 226 pound mole per hour, but they want it to be 191 pound mole per hour. They want us to modify our simulation such that it will be 191 pound mole per hour. Let me see that of the bottoms. The bottoms naturally is 774 pound mole per hour, but they want us to drop it to 365 pound mole per hour. So how do we do that? So basically, they want us to control these outlets. Let me raise this up a bit. They want us to control these outlets, the distillation, the distillate, and the bottoms. They want us to obtain, to set the value at 191 and 365. Sorry, let me remove this. Yeah. So they want to obtain they want the value to be 191 and 365 respectively. So to do that, we need to manipulate an input property. These guys are basically like state properties, or let me call them controlled variables. So we need a manipulating variable. So yeah, I want to manipulate. What do I want to manipulate? I want to wait, do we have a eta? Was there any eta specified? Okay, no eta. So I can manipulate maybe the inlet temperature, or I can manipulate the reflux ratio. I can manipulate a lot of things just to obtain the distillate and the bottom they require me to obtain. So let's say naturally this the process naturally is being supplied at 225 degrees Celsius and 250 psi. So I'm assuming that I can't manipulate this. If I can't manipulate the feed, then another thing I can manipulate is the reflux ratio. So let's see. Now, if I manipulate the reflux ratio, will I be able to obtain the 191 and the 365 distillate and bottoms they require me to obtain? So let's see how it goes. Now, to do that, this is where case study comes into play. With case study, I can vary my reflux ratio and I will monitor my distillate and bottoms rate. So let's see. Let's go. So case study. I have it here. Add case study. So my independent variable is what I want to vary, which is the reflux ratio. So let me find variable. I want to manipulate my reflux ratio. So yes, that reflux is at the condenser. So I'll come to coming. No. Okay. That guy. Bottoms, distillate, feed, no. Coming, feed block, feed up. What's this guy? Okay, I think I know what to do. So let me remove this. Let me, I'm coming. Sorry. So to put I want to manipulate something at the condenser. So I need the condenser to be shown here. So let me say I click on this. So this is the column itself. So and everything, every component of the column is now shown. Normally this is a template case. So I need the condenser to show. So this is the condenser over here. Click on it. So I need the reflux. I want to control the reflux ratio. So let me see. Where's the reflux? Okay, we have reflux control. Okay, let's see. So reflux control, I will add it. Condenser reflux. So done. No. This is not what I want. Let me delete it. Find variables. Click on this. Bring this condenser. Let's see. Here's the reflux ratio. This guy, okay, overhead mass, overhead, condenser overhead. This. Oh, has reflux ratio now here. Why is he not here? Coming? Sorry, it's not here. Buttons, keep on. Oh, sorry, we have reflux here. I have reflux here. So this is the reflux. So then I'll go and specify the okay, what can I specify? That will be reasonable with what we want to do. So reflux. Reflux. Refraction. Should I call it refraction? Flow. Sorry, molar flow. Oh, the reflux wants to be acting up. Well, let's do something else. If the reflux don't want to work, let's use the inlet temperature. Let's manipulate the inlet temperature. So the feed, and I want to manipulate the temperature. So I have this here. So I'm going to add this. This is inlet temperature, and what I want to observe is the distillate and the bottom's flow rate. So distillate, the flow rate. Okay, let me click on this so that I can molar flow. So I need distillate and the molar flow of this. Add another one. That's for the distillate, the bottoms too. I want the flow rate of the bottoms. So molar flow. Then here you go. Add it. So done. So now these are the current values. So I want to vary this value such that I can obtain 191 pound mole per hour at the top and at the overhead, and 365 pound mole per hour at the bottoms. So I've inserted my variable. So let's set it up. So the current value of my temperature is this. So let's say I'm starting from, let's say maybe 30 degrees Celsius to let me say 120 degrees Celsius, and at the step size of, let's say 10. Step size of 10. So let's run. It's running success. So let's come to results. So this is our value. So at the feed temperature of 30, this is the distillate molar flow, 102.5, and the bottom's molar flow is 351.1. Okay. So at the temperature of 40, this is 102.5. Oh, this we have just slight variation. Let me come to case study setup. The feed temperature is naturally 107.2. Okay, so let's come back. So okay, we have 102. We need a value of 191. This is not looking molar flow of this. Okay, these values are in kilomole per hour. So if I want it in pound per hour, let me just place my cursor on it. This is 225.9, 26. Actually, because it is in kilomole per hour, some errors have occurred in the calculation. If you look at this, is 225.9. This is 226. This is 226, 225.9. Oh wow. So okay. So 225.9. I need the value to be 191. So I guess I may have to, sorry. I don't like this, how this result looks like. Let me come back to case study. Let me come back to my flow sheet and see something. Sorry. So the current molar flow is 102.5, which is what was given to us as 102.5, and that's 126. Okay. So let me manipulate it manually without case study and see. So this is the inlet temperature. What if I reduce the inlet temperature to 90? Let's see what happens. So my simulation still converge. Let me see. Has anything changed in the? This is still 102.5. Composition, flow rate. This is still 102.5. Okay. 102.5. It means the inlet temperature is not really having effect. It means the inlet temperature of our distillation column is not really having effect. So we need to vary something else. So what else can we vary? Let's see. Okay, let me do something. Let's come back here. Let's see. Let's come to monitor. So instead of reflux ratio and vent rate that we specified, what if we specify what we are given exactly? We are given overhead flow of 191 and bottom flow of 365. So let's see what will happen if we specify those instead. So it means I'm going to be adding new specifications. So let's come to add spec over here. Add spec. So by add spec, I want to add a flow rate. So I'm going to be having column component flow here over here. So I'm going to add spec. So okay, it's here. Let me bring it here. So now, so which flow am I talking about? I'm talking about for the distillate flow, molar as basis. The value is the value they want it to be is 191 per mole per hour. So 191 per mole per hour. There you go. So then is none of, I want everything, like the whole distillate. So if you want a particular component, if what you want to specify is the flow rate of a particular component, you can select it. But what I want is just the flow rate of the distillate, which I've specified. So then the next one is the flow rate of the bottoms, which is 365. So add spec again. Add spec, components, column component flow, add spec. I can actually change the name. Let me say bottoms PTM flow rate. Okay. Now my draw rate is for the bottoms. Molar as my basis, and the value I want is 365 per mole per hour. Per mole per hour. I have it here. So let me change this name to distillate flow. Let me change this to distillate flow. So I have this guy. So let's cancel this. Now, instead of these two specifications that I was given, I want to change them to these two. So I'm going to unactivate this and this. Then I will activate this and this. So let's see one or more. So what's going on? It's telling us this guy is not fully defined. So what's not defined about it? Okay. Stream stage. What's not defined about it? Sorry. What's not defined about it? Sorry, not that quick. Run. Okay. Maybe we should let's add all bottom, everything is fine. Okay, let's add all the components and see. These, and this. Let me see. Run. It's going to give me the same. Let me add all the components to here also. These. No. So one thing about HYSYS is that immediately I insert a data that make it calculate that makes the calculation possible. It starts calculating. So, but I don't want it to be calculating because I still have some data I want to input. So I can let me stop this this simulation. So I'm resetting. So I will now, so that when I'm inputting data, it won't just be calculating when I don't want it to calculate. So I can come to home and put my HYSYS on hold. So if I put it on hold, it's not going to calculate anything until I put it on active. So I want to put it on hold. So let me come back to the monitor now. and come here and put all the come here and put all the components. So I want to put these two, this, and this. So now I've put everything. Let me put it back on active. So let's run and see. Will it run? Will you run? Will you run? Oh, this guy is not going to run. What's wrong? What's wrong? Okay, let's come back to our monitor. Let's uncheck this. Let's check what we were given previously. This and this, and I expect it to stop. Let's stop, reset, and run. So I expect it to converge. Stop. Stop, reset. So we have active this. What's going on? Okay, this and this. I want them inactive and I want this active. So converge. However, why are we not unable to manipulate the feed temperature? What's going on? What is going on? I'm coming. With the feed temperature is 194. Looks like coming. Sorry. Looks like, let me see what with feed temperature 194. And what do I have here? Okay, still the same thing. I don't know why I'm unable to manipulate the feed temperature to obtain the values they want us to obtain. But anyways, I will run the simulation again and send the keys to our WhatsApp group. So I'll manipulate any variable that seems manipulatable so that I can obtain the outputs I want. 191 pound mole per hour for the distillate and 365 pound mole per hour for the bottoms. So I'm going to do that and send that to our WhatsApp group. So that I won't spend much time on this. So that's it about distillation column. So we've successfully separated this feed into the lighter component, lighter ends, and the heavier ends. Lighter ends are the distillate, the heavier ends are the bottoms. And this is the beauty of Aspen HYSYS. If you want to do this by hand, it's going to take a whole lot of time because distillation column is a very, very non-linear process unit. So, and that is it about distillation. So I will do the manipulation and I'll send the case to the WhatsApp group. I'll send all the case we are doing also. I'll send everything to the WhatsApp group so that you can practice them on your own and check for can check if you're having any difficulty. So that's that about this problem statement. I don't know, do we still have time? Okay, it looks like we still have some time. So let's see. So that's problem statement 2. So let's go to problem statement 3. This one is simple reactor modeling. So we've dealt with separator, two-phase separator. We've dealt with distillation column and reactor. So these process equipments are some of the most important equipment in the chemical industry. Some of the most important equipment in the chemical industry, and I've strategically picked those process equipment for our practice. So we have simple reactor modeling. So how do we model a reactor? So let me share the slide. So sorry. Let me share this slide. So here you go. So simple reactor modeling. So how do we model a reactor on Aspen HYSYS? So let's quickly play around with that. In recent years, interest in hydrogen production from hydrocarbon has grown, driven by its importance in fuel cell applications. A key method is the partial oxidation of methane with air, producing hydrogen and carbon oxides via the reaction. So you have this reaction, we have reaction 1, reaction 2. The first reaction is partial oxidation of methane, and the second reaction is like complete oxidation of methane. Partial oxidation because CO is our product, it's part of our product. Complete oxidation here because CO2 is part of our product. So they want us to develop a simulation to model this process using Pengrobison fluid package at 25 degrees Celsius and 2 bar with feed molar flow of 100 kilogram mole per hour methane and 260 kilogram mole per hour air. That is 21% O2, 79% N2, and determine the outlet stream compositions. So this is just a simple reactor. So let's play around with it. So let me go back to let me share back my Aspen HYSYS. So share back my Aspen HYSYS. Present something else. Entire screen. Okay, share. There you go. So this is my Aspen HYSYS. So okay. So sorry. So now in recent years, interest in hydrogen production from hydrocarbon has grown. So of course we've been hearing about pink hydrogen, blue hydrogen, green hydrogen, this hydrogen, that hydrogen, gray hydrogen, and so on. Gray hydrogen, hydrogen that still contains CO2, blue hydrogen, hydrogen where the CO2 has been captured and sequestrated and so on. So basically those are the emerging energy source. All right, so we want to produce hydrogen from hydrocarbon. So to do that, these are the reactions that model that process. So the key method is the partial oxidation of methane with air, producing hydrogen and carbon oxides via these reactions. So let me go to my, okay, I am there already. So, okay, let me save this. Control, yes. Installation column. Practice. So, we'll ask you to do this one. Let me say this. Sorry. Okay, so let's open a new case. Let's open a new case. New templates. So here we go. So the first thing, like we mentioned earlier, is your component list. So let's list all our components. The components we have here are methane, oxygen, carbon monoxide, carbon dioxide, and nitrogen. So let's add. So methane, add oxygen. Sorry, oxygen. There you go. So we had CO. CO, add CO2, add hydrogen, say 2, add. So these are the components we are dealing with. So let's play added there. So let's go to our fluid package. Are we given any fluid package? Were we okay? Seems we are okay. Pengrobison, of course. So we're given Pengrobison as our fluid package. So fluid package, Pengrobison, and we've done that. So now we can go to our simulation. Okay, before we go to our simulation, since we are dealing with reactor, we have reactions. So I will now come to reaction here, reactions, to specify my reactions. So I have it here. So I'm adding. So it's going to give me a list of the type of add reactions, the type of reaction I want. Conversion, equilibrium, heterogeneous, catalytic, kinetic, simple rate. So the type of reaction I have here is just a simple conversion reaction. It's not equilibrium, and it's not heterogeneous catalytic, because I'm not dealing with a two-phase catalytic reaction. Yeah, it's not kinetic because I'm not using a kinetic model. So I'm going to be using, and it's not simple rate. I'm going to be using conversion, add reaction. So I have two reactions. So that's reaction one. So I add another reactions, because I have two reactions given in the problem statement. So for reaction one, so double click on it. So let me bring this here. Double click on it. So yeah, you're going to add all the components you want in the reaction. So the components I have, for the first reaction, I have methane. reacting with oxygen to produce carbon monoxide and hydrogen, H2. So stoichiometric coefficient here is where you are going to be specifying how your reaction actually looks like. So for the reactant side, your stoichiometric coefficient should be negative because they are being used up. While for the product side, your stoichiometric coefficient should be positive. So methane is at the reactant side and the coefficient is 1. So I'm going to be putting -1. Oxygen is at the reactant side, is part of the reactant. And the stoichiometric coefficient is 1/2. So I'm going to be putting -0.5. Hydrogen, CO is at the product side. So I'm going to be having +1. And hydrogen for the first reaction is +2. So I'm going to be having 2. So this is simply methane plus oxygen to give methane plus half oxygen to give CO plus 2 H2. That's basically this. Now, the next one is we are going to specify our base component. Of course, our base component here is going to be methane. So our base component is going to be methane. So I'm going to be specifying methane as my base component, which has been done automatically. Then reaction phase, I'm dealing with vapor phase because I have methane, oxygen, CO, they are all vapor. So I'm going to be putting vapor phase. Now, I want to specify my conversion. So what conversion of methane do I want? Methane is my base component. So what conversion of methane do I want? For the first reaction, it was stated that methane conversion is 40%. So I'm going to be putting 40%. 40%. And that's that. C1, look at it. The conversion is actually a function of temperature. But I'm just giving 40%, so I don't need to put that about these guys. This remaining 2. So, and that's that. I've successfully specified the reaction. So let's go to reaction 2. Reaction 2 is methane, CH4 plus oxygen, O2, to give CO2 plus H2. The stoichiometric coefficient are -1, -2 because it is -1, -1 because it is CH4 plus O2. So -1, -1 to give CO2, that's 1, plus 2H2, that's 2. And my conversion here for methane is my base component, my phase is vapor phase, and my conversion is 60% here for methane. And I'm green. So after specifying your reactions, which we've done, we come to reaction. Open a reaction set, click on the reaction set, add the reaction. So after you've added your reaction, I have 2 reactions, so I've added the 2 reactions. The next thing you're going to do is add to fluid package. So you add your reaction to fluid package so that whatever calculation you want to do will be done in that fluid package. So I add to the fluid package, which is Pengrobinson. So I add set to fluid package, and my simulation, my specification is ready. So I can now come to my simulation. I'll come to my simulation. Okay, so now I'm here, and it was stated that, so let's develop a simulation model to represent this process using Pengrobinson fluid package at 25 degrees Celsius and 2 bar with a feed molar flow of 100 kilomole per hour of methane and 260 kilomole per hour of air. Okay, and air contains oxygen and nitrogen. Don't forget that we did not add nitrogen to our components. So to do that, I'll simply come back to properties. Then I will come to component list 1, where my components are, and I will look for nitrogen N2. And here we go, we add it. So we added nitrogen. So let's come back to our simulation. So over here I have methane. So F4 to bring my model palette. Or let me just come here. View model palette. So I'm going to be bringing so I have 2 streams here from the question. It said with a feed, we have 2 streams, one containing methane, the other containing air, that's oxygen and nitrogen. So I'm going to be bringing in 2 streams. So the first one is methane. This one, methane. and the next one is here. So here, okay. So let's come back to this. So the temperature and pressure are 25 degrees Celsius and temperature 25 degrees Celsius and pressure of 2 bar, I think. Yes, 2 bar. So 2 bar. That guy. Okay, here we go. So then let's go to composition. So since we are dealing with, since this stream contains only methane, so the composition of methane will be 1. Every other thing will be 0. So okay, every other thing is 0. So I can come to my condition and put the flow rate of methane, the molar flow, which is 100 kilomole per hour. So 100 kilomole per hour of methane, and I'm green. So then for air, let me come to composition. The composition is 21% O2, so oxygen is 0.21 and 79% N2. So for nitrogen, it is 0.79. And okay, so I've imputed that. Okay, so the temperature and pressure are also the same thing, 25 and 2 bar, 25 degrees Celsius and 2 bar, 2 bar. Okay, and the flow rate was given to be 260 mole per hour, 260 mole per hour of air. So I'm going to be having 260 mole per hour of air. Is it more? Yeah, kilomole per hour of air, and I'll specify those two. So these two guys are entering my reactor. So the next thing is to do is to bring my reactor. So we have some different kind of reactors. We have conversion reactor, we have equilibrium reactor. So let me just type reactor. So think that we have a lot of reactor. This CSTR, this PFR, this conversion, this equilibrium. So we have a lot of reactors. So here we are just simply going to be using a simple conversion reactor. So I'm going to be bringing in this. So double click on that. Let's bring this. This is too big. Let's reduce the size. Okay. So now the inlets are methane.
Excuse me, sir. Sorry to cut you short.
Okay.
For the air, you actually inserted that of nitrogen into methane, I think.
Let's see. Okay. Thank you. Thank you very much. Look at me. Thank you. Thank you very much. So nitrogen is 0.79. Thank you very much.
From the point of somebody that doesn't know where
0.7. Okay, thank you very much. Okay, so methane is entering the reactor. Air is also entering the reactor. We have air entering the reactor and the outlet. So the outlet. So this reactor is not only acting as a reactor, it's also acting as a separator, a two-phase separator. So let me call this vape and let me call this loop. Okay, so now let's come to reaction. So we specified our input and output. Let's come to reaction. So we are going to add our reaction set. So that's set 1, which contains the 2 reactions we are going to be dealing with. See the 2 reactions, reaction 1, reaction 2. And this has converged. So let's fully calculate it. So let's see. Here are the vapor. We have this is our flow rate. Let's see the composition. So see the composition. Methane is 5.59%. No oxygen. Why do we have no oxygen? Because our oxygen was used up. Why was our oxygen used up? Because we had 1,000 mole of ethane and 260 mole of oxygen. Sorry. Okay, 100 mole of methane. Am I sure I use 100 or 1,000? Let me confirm, please. Okay, I use 100. So we have 100 mole of methane and 260 mole of air, which is 21% oxygen. So we have limited amount of air. limited amount of oxygen, I mean. So 21% of this will be very small. So that will be around 52 mole. So which means the oxygen was used up. And that's why I don't have oxygen here. So composition, oxygen is 0. CO, carbon monoxide produce this. That's the composition. Carbon. If I want to see the actual mole flow, I can just change my basis to mole flow. And I'm going to have the methane is 25.4, oxygen this. Can we see CO2 this, hydrogen this, nitrogen this. Nitrogen is not involved in the reaction. So the amount of nitrogen in the inlet will be equal to the amount of nitrogen we have here. Let's check that because it was not involved in our reaction. So let me bring this in. So composition. See the amount of nitrogen. Let me change the basis to mole flow. I have 204.5. I have 204.5 because nitrogen was not involved in our reaction. So initially I have oxygen of 54.6, but the oxygen has been used up. I have okay, well, 0 methane. This is the air stream. I want to see the amount of methane I have previously. I have composition, basis, mole flow. I have 100 mole of methane previously. Now I have 25.4. I have 0 CO because they are products. Now I have 40 CO. 0 CO2. Now I have 34.6 kilomole per hour CO2. 0 hydrogen. Now I have 149.2 hydrogen. So I have successfully modeled. So with this, we have successfully modeled the reactor for the production of hydrogen. So if you want to do some manipulations around this reactor, you can simply do that. So let's see the liquid. The liquid has a flow rate of 0, which is expected. Why is it expected? Because our reaction phase is in vapor phase, and all our products that we are producing will also be in vapor. So if you look at our feed stream, our inlet stream, let's see methane. Methane, look at the vapor phase 1. Let's see here. Look at here also 1. So our reaction, the 2 feed entering are vapor. Our reaction is occurring at vapor phase. So this the vapor, the liquid part of the product will be 0 mole, 0 kilomole per hour. Why? Because there's no liquid being produced. Everything produced is in vapor form. So, and that is that about reactor modeling. So we've successfully dealt with three important process equipment, which are separators, distillation column, and reactor. So you are going to be having a problem statement. Let me just show you that you are going to be playing around with as. So this is the problem statement: production of ethyl chloride. So this guy over here is a problem that requires the use of the last 2 examples we've done. You're going to be using a reactor and then a distillation column for your separation. Or maybe I'm going to be using a separator too. So I'm just going to be playing around this as your exercise, and if you can do this successfully, then you are good to go with Aspen HYSYS. You're just going to earn your skill better, solve problems, play around with questions, play around with Aspen HYSYS, and you will get better. So let me go back to my slide. Sorry, let me go back to my slide. Present something else. Entire screen. Okay, come on. So let's go to this guy. So this is the problem statement: production of ethyl chloride. So production of ethyl chloride as a problem statement, you're going to be playing around with this. If you can do this, then you are good to go. So you just have to play around with as much problems as possible. Think of processes, industrial processes, and try to simulate them, and you are going to get better. So let's see what do we have next. Anything? Oh, thank you. So thank you very much for coming, even with last week anomalies. I'm very, very grateful that you are still here. Thank you very, very much.